So in this video, we're going to start taking a probabilistic view of robotics. It turns out that we're not going to get very far in robotics unless we have some mechanism for dealing with uncertainty. The information from a robot's sensors never provides really accurate information about the environment. There's always noise in that sensor information. So if you're dealing with something like a laser rangefinder, for example, maybe sometimes it gives you really accurate information, but sometimes there are going to be reflections off shiny table legs or other sources of noise that mean that you can't take for granted that the information that's coming from that sensor gives you a completely accurate view of the state of the world. And the robot's actuators have the same issue, right? So I can tell the robot that it should roll forward 1 meter, but I can't rely on that happening exactly as I expect it to, right? There could be something in the way. Even if things go more or less as I expect, no robot is going to move precisely 1 meter when I send that command. There's friction involved and just a lot of uncertainty. So the question is, what's the right way of dealing with this? We could sort of wave our hands and try to buy a better sensor and just hope for the best. But the prevailing approach in robotics right now is to use probabilistic approaches. So use probability theory as a mechanism for sort of handling uncertainty in a principled way. So what we're going to do in this video is just give a very gentle kind of reintroduction. Probably all of you have seen most of this in discrete math class before, for example, to basic probability notation, and start thinking about a couple of really simple examples of what it would look like to apply these ideas to understanding sensor information. So here's our basic notation. We're going to be talking about random variables. So in this slide, things like A and B are our random variables that can take on, sometimes they're Boolean variables, so in this case A is a Boolean variable that can be either true or false, or they could be multi-valued random variables like B, right, which represents some color. And our function here, P, is going to be mapping from these variables to the probability that those outcomes will occur, right? So the probability that A is true is 0.9 in this case. Probability that A is false is 0.1. We're also going to refer to probabilities that look like this as prior probabilities, meaning that this is the probability of this event given that we don't know anything else about the world. So our belief or our probability about this event might change in the face of additional information. And we'll see what that looks like in a minute. So that's this, right? So conditional probability represents exactly our idea of what the probability of one thing is given that we have information about some other thing, right? So here's this example. The prior probability on a given day that I will end up being squished is very, very small, right? So 1 in 1,000 or 1 in 10,000. But if you give me this piece of additional information that I happen to currently be standing underneath a falling piano, right, that changes my belief in the probability that I will be squished today. It raises that probability up to 0.9. Here's our definition of conditional probability in terms of prior probabilities. So if I know the probability that A and B are both true, the probability of A given B is the probability of A and B over the probability of B. So here we go, Bayes' rule. This is where the money is. This turns out to be probably the most useful identity in artificial intelligence and robotics. And it's really handy because it gives us a mechanism for updating our beliefs on the basis of evidence. So what we might think of A here is, we might think of A as being something we want to know about the state of the world. So A might be, for example, the location of a robot. B is going to be then, in that case, information coming from a sensor. right? So what we're interested in knowing is, given that we picked up some information from some sensor, what does that tell us? How does that change our belief about where the robot actually is? And this identity tells us exactly how we can do that calculation. And what pieces of information do we need to know? Well, we need to have a prior belief about where that robot was. We need to have some notion of where we were to start. And maybe more interestingly, we have to have, if we're thinking of this in terms of sensor updates, we have to have what would be called a sensor model. So in this case, this is telling us what we think our sensor does given a particular state of the world, right? And we'll see a little bit more of a concrete example of this in a second. And then we need this prior probability of the particular sensor reading that we've seen. And that seems like an odd thing to require, but we'll see that it's easy to get that. So let's make that concrete. Let's just work through a little bit of an example. So in this example, x, we have a random variable x that can take on one of 4 values. And this random variable expresses the location of a robot in this very simple environment. So there are 4 rooms, maybe 4 locations in a hallway, A, B, C, and D. And we know that the robot is in exactly one of those locations. So here we're sort of illustrating our prior probability distribution over that location variable x. And what we're saying is it's a uniform distribution. So we believe that it's equally likely that x equals a and the robot is here, or x equals b and the robot is there, x equals c and the robot is there, etc. So the interesting question is going to arise when we get some additional information that helps us to disambiguate where the robot actually is. So we need a sensor, and we're going to assume that this very simple robot has a room detector, a room sensor. Now, if it could actually tell him what room he was in, then life would be easy, but it's not perfect, right? We've said that sensors generally won't ever give us perfect information. So this sensor is 80% likely to be correct. So if we're in a particular room, there's an 80% chance that it will tell us we're in that room. There's a 20% chance it'll tell us we're in some other room, and it will always be off by at most 1. So it'll tell us that we're in the room on the left with a 10% chance, or a room to the right of where we really are with a 10% chance. And there's no chance it'll tell us we're in any of the other rooms. And that probability will wrap. We'll assume that this robot is in kind of a circular environment. So in this case, if the robot is in A, this shows the probability distribution over sensor readings given that the robot is in A, right? There's a 0.8 chance it will report he's in A. That's the chance that the sensor will sort of tell us the right thing. 0.1 in B, 0.1 in D. And we can express that down here as a conditional probability distribution, right? This is the value of the sensor, which we'll refer to as Z. This is the true state of the world, which we'll refer to as X. So this conditional probability distribution we would call our sensor model. This tells us how the sensor works. So we can revisit Bayes' rule now in this context, right? This is exactly the equation we saw before, except now I've replaced x with z, or a with x and b with z. So z is our sensor reading, and x is our prior belief. So now in this equation, we're thinking of x as being this random variable that can take on 4 values. So now this prior distribution is that 0.25, 0.25, 0.25 distribution we saw before that tells us initially we think that there's a uniform distribution over room locations. Once we get a particular sensor reading, that number will come from this. So let's work. We're going to assume that the sensor reading we got was B. So our robot is in his room, he doesn't know exactly where he is, he runs his sensor and it says B. So now we have to run the calculation. So we need to calculate for all of the different rooms, how does this change our belief? So let's do room A first, we'll just go through in order. And we can just plug everything into Bayes' rule, right? So here's what we want to calculate. The first term in Bayes' rule here is just reversing these conditional probabilities, so z ends up on the left. So this is our sensor model, and we know that that's going to be 0.1, right, because that's an off by 1 error. We know that our prior belief that the robot was in room A was 0.25. So this is where things get a little bit, this is maybe the only tricky bit here. It's not immediately clear, right? Just knowing how our sensor works doesn't tell us immediately what the probability of seeing a B from the sensor is. So it turns out that it's not a problem. This value can be calculated from the other terms. So one way is that we can use this identity. So if I need to know the probability of z, and I know the conditional probability of z given x, I can sum up over all of the different possible values of x to determine the probability of z. Let me think of an intuitive way to describe what's happening here. So I want to know the probability that z is true, and I know all of these conditional probabilities about z given x. Well, I know that one of those x's has to be the case, so I add up all of those different possible x's, and that gives me, and I sum them up, the probability of that x being true times the probability of z being true, given that the x is true. And once I sum up over all of those possibilities, those are all of the different ways that z can be true. And maybe that's not the most intuitive thing. You can just accept that this identity is correct if you'd like. The simpler thing to do, and what will often make sense, because it's going to make the calculations a little more straightforward, is just to basically throw away that denominator. Right, here's Bayes' rule with the bottom gone, and just replace it with this constant, which I'm calling eta here. And the key observation here is that the sensor value that we're looking at is the same across all of the different possible outcomes that we're considering. So we can just treat that as a constant, and we know that something had to happen, right? We're going to end up with some x, so the probability has to sum to 1. So what we can do is just figure out all the possible outcomes for x, and then pick an eta value that makes sure that they sum to 1. And I think that's what we'll do in this. So that's what I'm doing. I'm throwing out the denominator here. I'm replacing it with this eta value. I'm plugging in 0.1, 0.25. The product is 0.025 eta. And then I perform that same calculation for the other possible outcomes, right? For x equals b, x equals c, and x equals d. So this gives me my new probability distribution over my position, given that I saw a b. So here's that new probability distribution illustrated. Unfortunately, it's got these stupid etas in here, right? So they're not really probabilities until I figure out the actual value of that eta, but we know that they have to sum to 1 because we know that the robot has to end up somewhere. So I just do a little bit of algebra to solve for eta, and I end up with an eta value of 4. Plug that in, and I end up with this distribution over locations, which is probably not very surprising, right? So it says there's a 0 probability that I'm in position D, which makes sense because if my sensor indicated I was in position B, I know that it can't be that wrong, right? So it might be a little bit misleading to see that these sort of exactly match the probabilities from the sensor model. But that's only because that initial prior was uniform. So if I got another reading now that told me that the position of the robot was B, this probability would go up even higher. It would end up above 0.8, right? If we think of going through all of those calculations again, right, the numerator of that thing would be, we would end up with a 0.8 times a 0.8, whereas these guys would be a 0.1 times a 0.1, so these would end up quite small, and this would end up quite a bit bigger. And as we continue to see the robot at position B, that probability will approach 1. So that's the gist of how we can, right, that's sort of the simplest possible example of how we can use a sensor, if we know the probabilistic properties of the sensor, to update state information. What we'll do next, not in this video, but coming soon, is we'll think about how we can apply this idea to probabilistic mapping.